Welcome to my channel. Today we're going to discuss how reinforcement learning conquered Atari games forever, completely changing what we thought AI could do. In 2013, something incredible happened. A team at DeepMind created an AI that learned to play classic Atari games better than any human. And here's the mind-blowing part. It did this without being told the rules. No instruction manual, no training examples, just raw screen pixels going in and game actions coming out. The AI looked at the exact same thing you and I would see when playing Breakout, just colored pixels on a screen, and somehow figured out not just how to play, but how to discover strategies that humans had never even considered. The score kept climbing, past amateur level, past expert level, all the way to superhuman performance. And remember, no one programmed the strategy. No one said, hit the ball here or aim for that corner. The AI discovered it all by itself from scratch.
So, how do you traditionally teach a computer to play a game? The old approach was explicit programming. You write out every single rule. If the ball is to the right of the paddle, move right. If it's to the left, move left. Otherwise, stay still. This works for simple cases, but it completely breaks down for complex games. How do you write rules for intuition? How do you program the gut feeling that tells you to aim for a certain spot? You can't. The reinforcement learning approach is radically different. Instead of rules, you feed the system raw screen pixels, literally just the colors at each position on the screen. Then there's this mysterious black box in the middle and outcome actions: left, right, up, fire. The system somehow learns to transform raw visual input into intelligent decisions. The big question is, can a machine actually learn strategy just from looking at pixels and getting feedback on whether it won or lost? As we'll see, the answer is a resounding yes. Let's understand the fundamental framework of reinforcement learning. At its core, you have two main components, an agent and an environment. The agent is the learner, the decision maker. Think of it as the brain. The environment is everything else, in our case, the Atari game itself. Here's how they interact. The agent observes the current state, which is the game screen. Based on that observation, it decides on an action, like pressing left or right. That action goes to the environment, which updates the game and returns two things: a new state showing what happened, and a reward, maybe +1 for hitting a brick or -1 for losing. Then the cycle repeats. Observe, decide, act, learn. This loop runs thousands of times per game, and through trial and error, the agent gradually figures out which actions lead to higher rewards. It's learning from experience, just like a human player would, except it can play millions of games without getting tired.
Now here's the key concept that makes learning possible: the Q value. Q stands for quality, and Q of SA tells you how good it is to take action A when you're in state S. But here's the crucial insight. It's not just about immediate reward. The Q value captures your expected total future reward, accounting for everything that will happen down the line. Imagine you're at the center of a simple grid. You can move up, down, left, or right. Each move has a Q value attached to it. Initially, these are all question marks because the agent has no idea what's good. But as it explores and accumulates experience, patterns emerge. Maybe moving right consistently leads to higher scores, so its Q value climbs to 0.9. Moving down leads nowhere good, so it stays low at 0.2. The agent's job is to learn these Q values accurately and then simply pick the action with the highest Q value. That's it. That's the core of Q learning. Estimate how good each action is, then pick the best one. But how do we actually calculate these Q values? This is where the famous Bellman equation comes in, and it's surprisingly elegant. The idea is that the value of taking an action right now equals your immediate reward plus the discounted value of the best action you can take next. Let me break that down visually. You get some reward right now, say plus 10 points for hitting a brick. That's the big immediate payoff. But there's also future value to consider, the rewards you'll get later. The catch is that future rewards are worth less than immediate rewards because the future is uncertain, so we discount them. If gamma is 0.99, then a reward one step in the future is worth 0.99 times as much. 2 steps out, it's 0.98. 3 steps, 0.97, and so on. The full equation reads, Q of S A gets updated toward R plus gamma times the maximum Q value of the next state. In plain English, my current estimate equals immediate reward plus discounted best future. This one equation is the mathematical engine that powers all of Q learning. So if Q learning is so elegant, why couldn't we just apply it directly to Atari games? The answer is the curse of dimensionality. Classic Q learning stores Q values in a table, one row for every state, one column for every action. For simple problems, this works great. But think about an Atari screen. It's about 200 by 160 pixels, each with multiple color values. The number of possible unique screens is astronomical, something like 10 to the power of 60. There's not enough memory in every computer on Earth to store that table. Even if you could store it, you'd never see the same exact screen twice, so you'd never actually learn anything useful. The solution? Stop trying to memorize every single state. Instead, use a function that can generalize. If you've learned something about screens that looks similar to this one, apply that knowledge here too. And what's the ultimate flexible function approximator? A neural network. Instead of a table with 10 to the 60 rows, we use a neural network with maybe a few million parameters that can generalize across similar states. This is where Deep Q networks, or DQN, enters the picture. The breakthrough idea from DeepMind was to use a convolutional neural network to approximate Q values directly from raw pixels. Here's the architecture. On the left, you feed in the game screen, just raw pixel values. This goes through several convolutional layers. These layers are perfect for images because they can detect patterns like edges, shapes, and eventually higher-level features like the ball, the paddle, and the bricks. The CNN progressively compresses and abstracts the visual information. After the convolutional layers, we have a fully connected layer that takes all those learned features and combines them. Finally, the output layer has one node for each possible action: left, right, up, fire, and so on. Each output represents the Q value for that action. The network is essentially answering the question, given this screen, how good is each possible move? The highest Q value wins, and that's the action the agent takes. One network trained end-to-end, going from raw pixels to intelligent decisions. But there's a problem with naive neural network training in reinforcement learning. When you learn from consecutive experiences, they're highly correlated. Frame 1 looks almost identical to frame 2. This causes the neural network to overfit to recent patterns and forget what it learned before. DeepMind's first key innovation was experience replay. Instead of learning from experiences as they happen, you store them in a giant replay buffer. Think of it as a database of memories containing millions of past experiences. Each experience is a tuple: the state you were in, the action you took, the reward you got, and the next state you ended up in. During training, instead of using the most recent experience, you randomly sample a batch of experiences from this buffer. This randomization breaks the correlation between consecutive samples. An experience from a million steps ago might be sampled alongside one from just now. This dramatically stabilizes learning. As a bonus, rare but important experiences, like finally breaking through to a new level, get reused multiple times during training instead of being seen once and forgotten. The second major innovation is the target network. Here's the problem. Remember the Bellman equation? We're trying to update our Q values to match the target of reward plus gamma times the best next Q value. But that target Q value comes from the same network we're updating. So every time we update the network, the target moves too. It's like trying to hit a moving target that runs away every time you get close. The solution is elegant. maintain two copies of the network. The online network is the one we're actively training, updating its weights constantly as we learn. The target network is a frozen copy that we use to calculate targets. We hold the target network fixed for a while, say 10,000 steps, then copy over the weights from the online network. This means the targets stay stable long enough for the online network to actually learn something useful before the goalposts move again. Stable targets lead to stable learning, and that makes all the difference. There's one more crucial concept: the exploration versus exploitation trade-off. If the agent always picks the action with the highest Q value, it might get stuck in a local optimum, never discovering better strategies because it never tries anything new. But if it only explores randomly, it never capitalizes on what it's learned. DQN uses epsilon-greedy exploration. Epsilon is the probability of taking a random action instead of the best known action. Early in training, epsilon is high, maybe 1.0, meaning every action is random. The agent needs to explore the game world and try different things. As training progresses, epsilon decays. It drops to 0.5, then 0.1, then eventually 0.01. By the end, the agent almost always exploits its learned knowledge, only occasionally trying something random. This gradual shift from exploration to exploitation is critical. It ensures the agent discovers good strategies early on, then refines and exploits them later. Try random things early, use knowledge later. That's the essence of epsilon-greedy. Now, let's look at the results, and they are stunning. DeepMind tested DQN on 49 different Atari games, using the exact same algorithm and hyperparameters for all of them. No game-specific tuning whatsoever. The human baseline is set at 100%. On Breakout, DQN didn't just match human performance, it absolutely destroyed it, scoring over 1,300% of the human baseline. That's not a typo. The AI found a strategy humans never discovered. Dig a tunnel through the side of the bricks and let the ball bounce around behind them, racking up points automatically. On Pong, Enduro, and many others, similar superhuman performance. In total, DQN achieved superhuman performance on 29 out of 49 games. And remember, this is the same network architecture, the same training approach applied identically to games ranging from Pong to Space Invaders to Sequest. This was published in Nature in 2015 and instantly became a landmark paper in AI history. DQN wasn't just a breakthrough for games, it sparked a revolution in AI that continues today. In 2016, DeepMind used similar ideas to create AlphaGo, which defeated the world champion at Go, a game many thought computers would never master. In 2019, OpenAI 5 beat professional players at Dota 2, a game far more complex than any Atari title. In 2020, AlphaFold used reinforcement learning principles to solve protein structure prediction, a 50-year-old problem in biology. And in 2022, ChatGPT used reinforcement learning from human feedback, or RLHF, to become the conversational AI we know today. The applications have spread to robotics, autonomous vehicles, recommendation systems, and scientific research. All of this traces back to the fundamental insight: let agents learn from interaction, optimize long-term rewards, and use deep neural networks to generalize across massive state spaces. The revolution started with Atari, and it's still accelerating. If you found this video helpful, please like and subscribe to the channel for more AI engineering content. Thanks for watching.